Today's lecture will be covering the frequency response of series RC circuit filters. The last lecture we talked about why the different dielectrics are chosen in a capacitor, and I was going to go over that, but I found this YouTube video that does an exceptionally well job on explaining capacitors, how they're built, and so I can't really add to this, so I put the link into here. They go over resistors, capacitors, several things. I would highly recommend watching this. But as we're studying the electrical filter, and it is a circuit that permits electrical signals having certain frequencies to pass from the input to the output while blocking all others. That is, if it filters out all frequencies but the selected ones that we want and we design around. There are three types of series RC filters, two that can stand alone, while the last is a combination of the first two. We will begin with the passive low-pass first order series RC circuit as seen in figure 1. And as you can see, the signal comes through here. The voltage output of this filter is dropped across the capacitor, and as the frequency goes up, the reactance of the capacitor goes down, and the reactance is the opposition to current flow. So while this is a high reactance, there's a lot of voltage being dropped on here, but as the frequency goes up, this becomes a short, bringing all the signal down to the ground. This is a passive circuit because the components within the circuit receive and process electrical energy but do not generate or amplify the signal. The output of this circuit is across the capacitor, and as the frequency of the input increases, the capacitor's reactance decreasing, steering the input signal to ground, as I said before. And as you can see in this plot here, our 3 dB point, which is the first cutoff, which is equal to the FC, frequency cutoff, is equal to 1 over 2 pi RC. And that's how you get that. And so it passes everything below the cutoff frequency. The second circuit is called a passive high-pass series first-order RC filter, as seen in figure 2. Now the capacitor and the resistor change the spots, swap spots, and the output now is across the resistor. But as the reactance of the capacitor is very high at low frequencies, no current passes through the filter. Now remember that the output here is across the resistor, and as the input frequency increases, the capacitance reactance decreases, allowing more input energy to drop across the resistor. Remember that while the input voltage is 0 frequency, the output voltage is 0 volts because the capacitor blocks direct current and only has displacement current, as we discussed in two videos before. The third type of series RC filter is the passive bandpass series first order RC filter, which is the combination of both the low pass filter feeding the high pass, as in figure 3 illustrates this. So we have our, this is not real intuitive. This is our low pass filter here, and remember it passes everything below our cutoff frequency. So that becomes our upper band of the boundary of our filter. And then the high pass passes everything above. So the FL will be our low pass, our high pass filter's cutoff. And as you can see that right here. And we want these to be equal because they act like a voltage divider, and they'll drop equal amount of power over each one. When we plot the output of this is theoretically this is our low pass, which is the high pass filter's cutoff, but that's FL, and that's right here, the 3 dB point, and a 3 dB point for the low pass filter is right here, which is our high frequency cutoff point. Notice that the two 3 dB points on the graph are at FL and FH with low frequency and high cutoff frequency. They are your 1/2 power poles and occur at the cutoff frequency for that circuit. The bandwidth of the filter is FH, the high, that's the cutoff frequency of the low pass filter, which is your high frequency, minus the cutoff frequency of your high pass filter, FL equals BW, the bandwidth. And the first thing to consider when designing your bandpass filter, we are going to design a bandpass filter that allow all the frequencies involved in the human hearing to pass. Figure 4 illustrates the frequency response of the human ear, which is from 20 hertz to 20 kHz. Okay, now we know our frequency range we want our bandpass filter to be at. So the graph tells us that our high-pass filter's cutoff frequency is FL, which is 20 hertz, while the cutoff frequency of the low-pass filter is FH, which is 20 kHz. Use this fact in equation 1, which is FC equals 1 over 2 pi RC, we can calculate our capacitance. The resistance will be determined by the input resistor needed to match our source, as well as the output resistor to match our load, R2. To achieve maximum power transfer from the input to the output, aka load, we want R1 to equal R2. You can think through this by starting with the low pass filter and remembering that XC1 reactance is very low at all frequencies above the 3 dB point at FH equals 20 kHz. That means it sends the signal to ground. And that XC2 is low at all frequencies above the 3 dB point at FL equals 20 Hz. This causes R1 and R2 to act as a voltage divider and dropping the same voltage across each. This also causes a 6 dB drop across the bandpass filter. Can you tell me why? This can blow your mind, but just remember that the low-pass filter is from 0 Hz to 20 kHz, and the high-pass filter is everything above 20 Hz to infinity. I went ahead and opened the PTC Math Cad and did the calculations for continuity in our lab, so we will open up and actually construct this equation in our Math Cad. But R1 equals 100, R2 equals 100, the low pass filters FC is equal to 20 kHz, the high pass filters FC is equal to 20 Hz. We know our equation is FC equals 1 over 2 pi RC. We switch the capacitance with the frequency because we know the frequency, and we solve for the equation. Bring the C up here and the frequency down here, and we know that C1 is going to be 79.58 nanofarads. I move this over to the right one. That means I need to bring this to 9. C2, do the same thing. Swap the frequency with the capacitance. Solve the equation, and C2 becomes 79.58 microfarads. These microfarads is a more common value of a capacitance. And so 79.5, we bring the decimal point over to the right one. That means we raise this up one because that's how many spots it's over here. Okay, now we're going to build the circuits and use the QUCS and plot the output and check our results. This is going to be fun. So we can use the same circuit you used in video 110 and swap or put the capacitance to the 79.6 nanofarads and the resistance to 100 ohms. We want to sweep the frequency sweep from 10 hertz to 20 kHz at 301 points. This can stay the same, but we're just concerned about this graph right here. And as you can see, as we sweep from 20 hertz to 20 kHz, which is right here, that's our 3 dB point right there. So that's your low pass filter. Continuing to the high pass filter, we swap the positions of the resistor with the capacitor. We change the capacitance to 79.6 microfarads. The resistor is 100 ohms. We hit the simulation, do the same sweep, and now we can see the high pass filter with the 3 dB point of the FL at 20 hertz, FC at 20 hertz, and that's right there. It's cool. Now we're going to combine the two circuits to make our bandpass filter. So we have the C2 right here at 79.6 nanofarads, C1 at 79.6 microfarads, R2, this is R1 actually, is 100 ohms, R2 is 100 ohms. Sweep the same frequency range, 10 hertz to 20 kHz at 301 points, and we get the exact same plot that we saw up here when we did our bandpass filter. The reason why this is 6 dBs down, from right here, exactly 6 dB down, because it is a half power point for voltage. It's it's the half voltage point. 3 dB is for power, 6 dB is for voltage. So that's why that's there. And so we can see that from 20 hertz to 20 kHz, it goes a little bit further, but it didn't quite make it to 20 kHz, but it's very close. And that's that. So as you can see, the frequency response plot is a very important tool for the analysis of circuit behavior. This plot is called a Bode plot and gives us a feel for the frequency response of a circuit with respect to amplitude and phase. This type of graph was the result of the pioneer work done by Hendrik Wade Bode, and he did his research at Bell Labs. They got left off somehow. Okay, but he worked at Bell Labs. Here's another Bode plot. It's a low-pass filter, 3 dB point. And this has a 20 dB attenuation per decade and 6 dB per octave, which goes right here. And we'll go into that more on other lessons. Here we show you the first order, second order, third order. What we just reviewed, there was all first order. It means it has one pole. As you increase the number of poles, your attenuation increases greatly, making the edges of your filter sharper. So more of this will be covered later. That's it. So now for the lab. Don't forget to select subscribe and hit the like button if you enjoyed this video.